So welcome to the 23rd lecture on the proof complexity as a computational lens course, where interestingly we're not going to do any proof complexity. I think this is maybe the first lecture where we actually completely skip the proof complexity. We're just going to do communication complexity. We're going to prove a simulation result, how communication protocols can be converted efficiently to decision trees. Or at least we're going to simulate as much of this proof as we can, and then at some point you or I will run out of energy. Let's see what happens first. But the context, so let's just see why it is a proof complexity result. So what are we doing? So we're doing size space. Our excuse for doing this is that we are trying to establish size space trade-offs for cutting planes. And what did we do last time? With a lot of vigorous hand waving, we showed that short space efficient proofs can be used for round efficient protocols for search F. Okay, so if I have a proof for establishing the unsatisfiability of a CNF formula F, that gives me a round efficient protocol for the search problem given a truth value assignment, find a falsified clause in F when the variables have been distributed in some way between Alice and Bob. In particular, we defined lifted CNF formulas. Lift L of F, where the fact we'll talk more about lifting today, but the point was that then we argued quickly that if we have a protocol for search, the search problem for this lifted CNF formula, that also works for a lifted search problem, namely for lift search F. And this is the problem that we need to care about today. So what is this? So a search problem, which for us will be total. Actually, let me write it down here. So we had a total search problem. Our problem will always be total. Is a relation S with inputs in Z and outputs in Q, and basically the search problem is given Z, find a Q such that Z Q is in the relation. And the point is it's a total search problem if for every Z there is at least a Q. We are focusing on the input domain being 0, 1 to the M from now on. Okay? And in particular, the falsified search problem when written in this way is the input Z is a truth value assignment, and the output Q is, say, the index of a falsified clause. So now
search of lift of L and lift L of search are the same problem, right? Because you just
no. So this is a CNF formula.
Yeah.
This is a search problem for a CNF formula.
Yeah.
Okay. This is a search problem that is lifted. But we're only going to talk about the lifted search problem, so let me define it now. Okay. So for a search problem, what we do to define, so we have a search problem, a total search problem, S, we lift it by length L by basically doing the following. For every coordinate, Alice gets an index, so she will get an array of integers between 1 and L. Bob gets bit vectors of length L, m of them. Okay, and the point is now that for every coordinate, Alice's integer tells us which position in Bob's bit we're interested in. And the task in a lifted search problem is to find a Q such that, so the input is X for Alice, it's a Y for Bob, and we want to find a Q such that when I use X to index in Y, I get a Z such that ZQ lives in the relation. So, and just to make absolutely sure we're on the same page, so what is this indexing thing? It's exactly what I said. If xi is an integer and yi is a bit string, then this is basically just saying that I want the coordinate specified by x. And then if x and y are vectors, then the indexing of that vector is just that I apply indexing in every coordinate. So an x1 chooses a bit in y1, x2 chooses a bit in y2, and finally xm chooses a bit in ym. Okay? So far what we did, we said that if I took the right type of CNF formulas and generated a new syntactic object that was a CNF formula, a lifted CNF formula, I had a short proof for the unsatisfiability of the CNF formula lift F. Then that gave me a good protocol for the search problem for lift F, which by an easy transformation I can actually use not for the search problem for the lifted formula, but for the lifted search problem for the original formula. Okay. So from now on, we're only going to talk about lifted search problems. And in fact, from now on, S is not going to be a falsified closed search problem. We couldn't care less. It's any search problem. The one thing that is important is that the domain has some kind of coordinate structure. Okay, so for us, it's bits. Okay. And then the missing piece, on the other side, we also saw then that there exist pebbling formulas for which the falsified closed search problem, or just the search problem, cannot be solved by shallow decision trees with few queries. With a small total number of queries. Okay, this is something we sort of mostly hand waved this, and you took it on faith. So now the missing piece is to connect communication complexity. So on the one hand, we're getting an amazing communication protocol, round efficient, for a lifted search problem. On the other hand, we know that there cannot be shallow query efficient decision trees. Okay? And in order to put this together into a trade-off result, we have the missing piece that we're going to do today, which is that if we have a round efficient protocol with small total communication, for the lifted search problem. Okay. Then, from such a round-efficient, low communication cost protocol, we obtain a shallow decision tree with small query complexity for the original search problem. Okay. So this is what we want to prove. We want to take a round-efficient protocol that has few rounds and small amount of total communication and turn it into a decision tree. If we can do this, then the pebbling formulas and the short space efficient proof are going to collide. Okay, and that is what will give us. So basically, we just run this backward and say that since there cannot be any shallow query efficient decision tree, there cannot be an efficient protocol, and therefore there cannot be short space efficient proofs, and that tells us that we have a trade. And then separately, we also prove upper bounds where we exhibit space efficient and short proofs, but this we kind of ignored. Okay, so this is what is referred to as a simulation theorem. And in order to get it for full-blown cutting planes, we need to do this for real communication, but it's going to be, we're going to have to sweat enough today. We'll just do it for standard deterministic communication. So strictly speaking, what we do today will be sufficient to get trade-off results for cutting planes with coefficients of at most polynomial size, at most a logarithmic number of bits. But like all of the main degrees are there, and actually some of the main technical lemmas will be stated so that they work also for the real communication case. So we're just, we cannot deal with all complexity in one go. So we'll just do it for deterministic communication. Yes?
Since we're talking about search problem, do you know, because I don't actually know that, but like, do you know to what TFNP class pebbling formulas correspond?
I know that pebbling formulas have been used. I probably should know. Embarrassingly, I don't.
I don't.
But I mean, I think they've kind of been. I just don't know. Sorry.
Okay, no worries.
Very embarrassing, but yeah, I should. Okay, so what is our idea? So we are going to run the round efficient protocol. Basically, so we just.
It's in CLS.
Say again?
Sorry, I think it's in CLS.
Oh, okay, that's cool. Okay.
Let me check. Because you have to say where the path ends and somehow. Sorry, you're just answering this question. If I remember correctly, it's in CLS. We have to say when this blue path ends. And that somehow corresponds to the maximum. You have to find the lowest vertex in the blue path.
Okay.
That's like a maximum element.
But do you know if it's CLS complete?
Yeah, it's all. No, I don't know if it's CLS complete.
Okay, okay. Well, we can
That's
try.
why I was answering.
Okay.
Thank you.
Good. So what are we going to do? We're going to take basically, we're going to build an algorithm that takes a good protocol as input, as offline input, and then uses it to compute which queries it wants to issue. So we're going to describe an algorithm that is a decision tree, but it computes which queries it wants to issue by running the communication protocol. As we discussed last time, there's a problem. We have no idea what Alice and Bob's inputs are. So we start out with knowing nothing. Alice's input could be anything, Bob's input could be anything. And what we're going to do, we'll simulate the protocol by basically trying to send maximally uninformative messages. Like at all times, we're sending just bits. So both when Alice and Bob speak, they divide their set of consistent inputs in at most a half. And we're going to always pick the bigger half. Okay? And then we might need to do some cleanup to have these sets of inputs that are consistent with the communication. So far, we want them to have some nice structure. Then what will happen is when on some coordinate, where Alice has on some coordinate Alice has some Alice has some choice of integers L, and Bob has tons of bit strings, but we're going a little bit somehow a coordinate is starting to look constrained. At that point, we say, oh, I have to issue a query to the decision tree, and then the decision tree makes the query, we get back the value, and then we have to clean up Alice and Bob sets to match that. Now we only want to have X i's and Y i's left that actually match the bit that we got from the decision tree. Okay, and the name of the game will somehow be, obviously we don't want to issue queries. We'll only be forced with kicking and screaming, and we want to argue that anytime we issue a query, we can afford to do so because there's have been a lot of communication going on. That would be the game. And also, the extra twist compared to standard simulation theorems for us would be that we have to do this in a round efficient way. In the standard simulation, as soon as a coordinate goes low, we issue a query to the decision tree. And then we clean up and then we continue. Now, if we're in the middle of a round where Alice is speaking, we can't afford to issue the query. We have to somehow, a coordinate has gone low, we're in serious trouble. We just make a mental note that, okay, I'll have to query I, but I hope Alice stops speaking soon. Okay, but then maybe she continues to speak and some coordinate I prime also goes bad and I double prime, and we just take note of this and desperately clean Alice and Bob's inputs, anticipating that we will then make a batch query to coordinates I prime, I double prime, and then somehow deal with the cleanup all in one.
Sorry, so if the round number of rounds is R and total communication is C, what depth are you trying to?
I'm going to state precise theorem in a little bit. So basically, we want to match the parameters. So let me start setting up notation. Some of it. So throughout this lecture, so we maintain a set of indices. So again, recall that our input, the original input Z, lives in 0, 1 to the m. And I, living in integers from 1 to m, is the set of non-queried coordinates at all times. These are the coordinates for which we have maintained enough uncertainty that we haven't had to issue a query. Whenever I write S and A and B will be sets of vectors. On Alice's side, they will be vectors of integers. On Bob's side, they will be vectors of bit strings. Whenever I write S sub I, that means that the vectors in S live in I. So I'm restrict them to the coordinate set I. Okay? Just a piece of notation, I will repeat this. When I don't want to, so this really changes S, like I throw away everything outside. Another operation which does not throw away things in the same way is if I don't want to change S, I can just take S and then project it down to these coordinates. So this is the projection to I. Okay. And these both live in the same space, but this one potentially lives in a much larger space. Like this could live, this could have vectors in all the way from 1 to m. So now we have our example from last time. So how do we measure? The important thing is going to be how to measure when a coordinate becomes too constrained. We're not going to worry so much about Bob, because Bob doesn't have much information. He just has a gigantic set of bit strings. It's a very long set. The lift length L is going to be m total number of variables cube plus a bit. So Bob will have a very hard time to convey anything meaningful, even about a single coordinate. So we're not worrying so much about Bob. We are worrying about Alice. Because if Alice somehow conveys to Bob that, in her position, her x1 is 42, then Bob knows that, she's only interested in bit 42. And then, of course, whatever Bob has there had better, then that must, if that happens, the only way that can happen is that we somehow know that when the decision tree queries Z1, it has to get the same bit back. because otherwise our simulation will fail. So we will be very interested in keeping track of how constrained Alice is in coordinate I. And the way we do this is by looking at the graph in coordinate I for Alice's sets of inputs, where I'm interested in, note that I'm only now looking at the inputs for the coordinates that are live. So this is what, whenever I have this notation, it means that A has integers in this index set only. Okay? So the graph I of AI has left vertices, integers, okay, which you should think of as the ith coordinate. The right vertices are all other coordinates. So L to the I minus little I. And then I have an edge between xi and xi minus I. This is a lowercase x, this is an uppercase x. If the concatenation, if xi, sorry, this is not, sorry, all of them are lowercase. I'm just confused today. These are lowercase are vectors, so if the concatenation lowercase xi minus little I concatenated with xi, where this concatenation sort of makes sure that all coordinates end up in the right places, if this is in AI. Okay. So this is a graph, and happily we have our example from last time. Suppose that AI is, so now L is 3, and suppose that Alice's vectors are 1, 1, 1, 1, 1, 2, 1, 2, 3, 1, 3, 1, 1, 3, 2, etc. And suppose I want to do graph 1, then on the left-hand side, I have 1, 2, and 3, corresponding to the possible values in the first coordinate. On the right-hand side, I have all possible 9 options for coordinates 2 and 3. And whenever there is a completion, for instance, 1, 1, 1 gives me the edge between 1 and 1, 1. 1, 1, 2 gives me the edge between 1 and 1, 1, 2. 1, 2, 3 gives me the edge between 1 and 2, 3. Okay? So this is just a graph representation of AI that somehow gives me interesting information about the ith coordinate. And now what I want to happen is, like I'm saying that coordinate I, I'm happy about coordinate I if, suppose that the worst possible case happens. Alice somehow has to reveal all other coordinates. It turns out that all other coordinates are like 2, 3. Even in that case, I want there to be a lot of wiggle room with respect to what index Alice has in coordinate 1. How do I know if there's a lot of wiggle room? Well, the right degree, right? Here you see if Alice fixes the rest of her vector to 2, 3, then actually she could complete this to all possible coordinates. So this is a very good scenario. However, if I would have if I have a vertex of degree 0, this I don't worry about, because then I know that there is no such string in Alice's input to begin with. But what I would worry about if there are right vertices here of low degree, because then that means if Alice is for some reason forced to commit to that string for the other coordinates, then by that time we're already fixing the final coordinate, and maybe Alice and Bob will figure it out without communicating, which means that I can't afford making the query, but I will need to make the query.
AI is the part of Alice's rectangle that we are simulating.
Yeah, you can think of it as, yes.
So AI is like pi I of S.
Actually, AI will always be pi I of A. So I will maintain Alice's inputs over all coordinates. And then whenever I look at the graph, I will always just project to the current index set I of remaining coordinates. So you will see a lot of pi I of A's. That's sort of always what will happen. Okay, and now, so two important notions is the average degree of this graph, and this is just the average non-zero right degree. And then I have min degree, which is what I'm mostly worried about. And that is the minimum non-zero right degree. And my definition is going to be basically, I'm going to consider the average degree to be good if it is at least L raised to the power of lambda. I'll fix lambda a little bit later, but you could think lambda is basically 1 minus some small epsilon. So on average, I want almost full completion. Okay, but in order to be able to perform the simulation successfully, I need to worry about the min degree because I'm doing this worst case. Okay. Let me say one more thing before I erase this picture. So one thing that will become important later on is, suppose I'm looking at the graph of AI for coordinate I, and suppose I remove some other coordinate. For instance, here, suppose I remove coordinate 2. Okay, and now I can look at the graph 1 of A restricted to I minus index 2. How does that change the right degree?
It gets up.
It can only get better. It can only get higher because what happens, if you look at, I remove coordinate 2, then 1, 1, and 2, 1, and 3, 1 will merge into a single vertex. And 1, 2, and 2, 2, and 3, 2 will merge into a single vertex. So here you see you have a lot of degree 2 guys, some degree 3 guys. Actually, here's the graph when I project, when I project and remove index 2, and you see now I get the complete graph. Okay? So we're going to use that when you project away a coordinate, the right degree can only improve. Okay, so now I want to describe to you, oops. Any way of convincing this not to move so much? So now our goal is to define the simulation algorithm and then try to, in a top-down manner, prove correctness and see how far we can get. Okay. So what do we do when our degree is going low? Well, then it turns out that what we need to do is to restrict the possible inputs for Alice and Bob in the coordinate that has gone bad. And I'm going to focus on Alice, but we need this for both Alice and Bob. So the restriction in coordinate I to a set of possible indices U, so here U lives in subset L, okay, of A. That is just, I take all the x's in A such that in coordinate I, the value of Alice has to live in U. And similarly for Bob, rho I v of B is just all Bob's vectors y, such that in coordinate y I, you're lying inside capital V, which will now be a set of bit strings of length L. Yeah? Then I need to manage, like, once Alice has committed to, so Alice has proven, and now she knows, say, that she's maintaining that her values is something in U. And now I want to be able to ensure that whatever value in U Alice has, Bob can actually answer with a B, okay? Which is a bit. And this definition will be, so now this is a bit string. These are all bit strings W in 0, 1 to the L, such that for all coordinates J in U, Wj has bit B. Okay. I'll give you one more definition, then maybe if you want to see examples of this, we can do examples. I think it might be enlightening examples. So here's the final key notion that we will need. So we will need to look at Bob's inputs. And given that we have information, we're looking at coordinate I. Bob, Alice has committed to that she has one of her indices her index is one of the integers in U, and we want to be able to deal with a decision tree returning bit B. In order to do so, we can take chi b I u of B, which is just projecting in the ith coordinate to all bit strings that have bit B in all coordinates U. Okay. These are going to be like super important notions. So is it like it's all crystal clear, or should we like do a small toy example just to get a hang of what this is? I was proposing to do a small toy example, maybe.
Yeah, maybe for chi b. I don't.
So let's just So here's an example. Let's fix I to be 4. We have 4 coordinates, 4 Boolean variables in the original input set. Let's fix L, the lift length, to be 5. And suppose that U, the coordinates that we're interested in, are 1, 4, and 5. Okay. And now suppose that AI is 1, 1, 1, 1, 1, 2, 3, 4, 2, 3, 4, 5, 2, 5, 5, 2. These are right. Alice's inputs will be 4 tuples of integers between 1 and 5. I don't know. 3, 2, 1, 3, 3, 4, 5, 3, 4, 4, 4, 4, and 5, 4, 3, 2. Okay. Suppose we're at a stage where like these are the inputs on Alice's side, which are consistent with what has been communicated so far. Then to get rho 1 U of A, this will now pick out all the vectors for Alice where the first coordinate is 1, 4, or 5. Right? So these two guys survive, 1, 1. The first coordinate is 2, so this goes away, this goes away, this goes away, these two survive. Okay, so these are the kind of operations that we will do cleanup operations. Does this operation make sense? So again, I'm looking at a set for Alice. Oh, there should be an I here, right? Where everything. Okay. And in coordinate y, I'm saying only look at coordinate y and remove from A anything that in coordinate y does not have one of the integers in U. This. Okay. The 1, 2, 4, and 5 survive. 2 and 3. If you have 2 and 3 in the first coordinate, those vectors will die.
Where does V live?
V, we're getting to V. So V lives in 0, 1 to the L. So V1 of U will be all bit strings of length 5 where, okay, so maybe I'll do this with a B even for B is 0 or 1. What are the bit strings that are fixed to B in the coordinates in U? Well, that will be in coordinates 1, 4, and 5, I want a B. This could be where B is 0 or 1, right? And then in all our other coordinates, I'm free. Am I making sense? So it's just saying, give me all the bit strings except all positions in U should be fixed to B. Okay. And finally, a small example. Suppose now that B it's getting a little bit annoying to write because B are now consists of bit strings of length 5, 4 in every vector. So bear with me. Suppose we have 4 vectors. One is the all 0. Missing a coordinate. This is a valid B vector. We should have 4 coordinates. All of them should be bit strings of length 5. Suppose the next one is 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 0. Say, okay, I'm not following my own notes even. This will be dangerous. 1, 0, 0, 1, 1. 1, 0, 1, 1, 1. 1, 1, 0, 0, 0. 1, 0, 0, 0, 0. 2 more. 1, 0, 1, 0, 1. 0, 1, 0, 1, 0. 0, 0, 0, 0, 0. 1, 1, 1, 1, 1. So far we have 4 B vectors, right? Each row is a B vector, and let's just do a final one. 1, 1, 1, 1, 1. 1, 1, 1, 1, 0. 1, 1, 1, 0, 0. 1, 1, 0, 0, 0. Okay. Suppose this is BI. The final thing we need to understand is, suppose now that I look in the first coordinate and I insist that in all coordinates specified by U, I want to have a 1. Okay? What is this then? This is, if we can understand this, then we're in good shape. Okay? So U is going to look at coordinates 1, 4, and 5. Right? And now, since I'm asking that in all these coordinates, I want the bit to be 1, those of Bob's vectors that don't satisfy this, they will go away. The ones that do satisfy this, they will survive. So here for Alice, we had row 1u of A were these two. Here for Alice, we see that we want all the red marked coordinates should be ones, right? So this one clearly goes away, this one goes away, this one survives. This has a 0 there, so it doesn't survive, and this one survives.
So the one in the subscript indicates which
This is the coordinate.
bit string you're looking at.
Yeah, this is the coordinate. So this was like, this one here is that one. So chi2u1 would have looked at this coordinate. Okay?
So this means if Alice's first index is restricted to be in U, then you can respond with B.
So this in particular means that, yeah, so if suppose that, so the nice thing with this, okay, suppose that Alice now has committed to that in coordinate 1, she has an integer in U. I don't know which, okay? And suppose we queried the decision tree and it gave us back a 1. Then in order to make sure that the indexing operator will be consistent for Alice and Bob, this is exactly the set that Bob will want to keep, because he just knows that at the end of the day, Alice says that in the first coordinate, she has an integer from U, right? And we know that the decision tree apparently said that we wanted a 1. So whatever integer Alice reveals in the end, I have to be able to respond with a 1. Then this is the set that I want. Okay, then we're actually, it's time to write down the simulation algorithm. Okay, so the algorithm that takes a protocol pi and evaluates Z. It will query said this algorithm is supposed to output a Q such that ZQ is in the relation S. Right? The output of this guy is a Q such that ZQ should be in S. Okay? So what do we do? See if we can fix I'm a little bit unsure about the column width, but let's do our best. So we start by just initializing. We're saying that Alice's input could be anything, L to the M. Bob's input could also be anything, right? So 0, 1 to the LM. We have not queried anything. And we start at the root of the protocol tree. Okay? Now, while V is not a leaf, when we reach a leaf, we have to issue an answer. But while V is not a leaf, we do the following. So now we initialize. Q is are the coordinates that we need to query in this round. We're going to have an auxiliary set CI. And that is basically, so the problem is, again, the action is going to happen while Alice speaks. While Alice speaks, that's when her coordinates go bad. That's when we're going to say, oops, we need to query more coordinates. However, we cannot query. Okay? So what will happen is that as we accumulate more and more indices that Alice says needs to be queried, Bob is basically going to be very busy applying this chi thingy to make sure that, okay, yet one more coordinate, and I need to be able to answer both zeros and ones. And to maintain this, we're going to have a proxy index set C. Note that it lives inside I. So A and B will always live over all coordinates. C lives only in I. And I initialize it at the start of every iteration of the while loop to just project Bob set to the current coordinates that are still active, that we haven't queried. Next step. While Alice speaks at V, then we need to check, are we in good shape with our coordinates? Okay. If there exists an I such that the average degree, and note now that here's exactly this thing we talked about before. A and B are always going to live in all of M throughout the algorithm, but I'm projecting them down to the remaining coordinates because that's where my graphs live. For coordinates outside of I, at this point, I have already committed and everything is fine. Okay. So if the average degree is too low, smaller than L to the lambda, where again lambda was 1 minus some epsilon, this means now that some right vertex somehow, the right, in this coordinate, it seems like things are a little bit too constrained. Okay? So then, what I do is, Alice will now commit to, let me switch colors, she will find a good set of integers and basically promise that in the ith coordinate, I will only support these values. Okay, how will we find such a set? It's magic. And in fact, this is the hardest, this is probably the theorem that, well, in a minute, I'll tell you what the properties are. We might not be able to prove this. I don't think we will have the energy to do it. So somehow the intuition is that this is a good set for Alice to commit to because things will now be so basically what happens, so I is a coordinate that has gone low. At this point, Alice decides that I have to, we have to issue a query to I. There's no avoiding it. Okay, this is what's happening. We have to query I. It's time for a decision tree query. So now I need to prepare, right? Alice wants to keep as many coordinates as possible, but in all of these coordinates, Bob needs to be able to support whatever the decision tree gives back to us. So this is what we're doing now. So on Alice's side, I am now saying I'm trimming A so that in coordinate I only have these values. On both sides, for B, bit B being 0 or 1, because we don't know what we're going to get back, I'm going to set CB I minus I. And again, note that this now indicates that this C vector is going to live in a smaller space. This is what this subscript that's what this subscript denotes. So what I'm going to set this to, I am going to make sure that I can support in the ith coordinates on all indices UI, I can support this bit. And then once I'm sure of this, then I don't need to worry about this bit any longer. I just project it. I project away this coordinate. Okay. So this is the set. So note that in the ith, this is the set of in all other coordinates where I know that on any coordinate that Alice has in UI for index any index in UI that Alice has for coordinate I will be able to complete to a B. But I don't know what the decision tree will give me back, right? Is it a 0 or a 1? And I won't know in quite a while. So therefore, I will set CII to be the intersection. Note that we have, in this set, we have moved away the ith coordinate, but since it is the intersection, we know that for any vector that lives in here on the other coordinates, in the ith coordinate, I will be able to complete both to 1 and to a 0 on this coordinate, on this index set of values. And now I have sort of officially declared that I've given up on coordinate I. So I shrink capital I. And I make a note that we have to query coordinate I. So this line 6 is project, and then all of the things that happens here is numbered as line 7 in the pseudocode, and I feel like I don't feel confident to mess with the pseudocode numbering, so I'm going to stick with it. Okay, now we're done. When we're exiting here, the dust settles. I know now that I've pruned Alice's set. So that I've given up on a bunch of coordinates. There are 2 constraints. In all other coordinates, average degree is looking fine. So now it's time for Alice to speak her bit. So she has to speak a bit B. What should she speak? Well, she has 2 possibilities. So a piece of notation. Okay, did I write this? So let's see. So let's say that XV are Alice's inputs consistent with the node V in the protocol. So XV is like everything that Alice could possibly have if they've reached this far in the protocol. And same thing for Bob. Just a piece of notation. Is this making sense? I think maybe I didn't write this. I forgot this. I wonder if there's anything else I forgot. We'll find out. Okay. So basically, I'm picking now. I know I'm going to go down to, and VB is the node I get to when Alice speaks bit B. So which one of them should I choose? I know that A is going to shrink, obviously, by this intersection, right? What's the least informative thing? Well, the least informative thing is the B that maximizes the size of this. So I pick that B, and then I say, this is what Alice speaks, and let's, in the protocol tree, move to VB. Okay. I do one more magic thing also. Sorry that I inserted in between, just to be fully in sync. VB. This was line 7. This is line 8. This is line 9. So what happens now is that I don't have control over how this intersection will affect A, and maybe it will mess up the structure a bit. So therefore, I will clean up A at this point. I will prune A intersection xvd. With respect to the currently active set of coordinates. Okay. So this is, as long as Alice speaks, we do this. We check, is there a coordinate that has gone bad? Then we schedule it for querying. We clean up on Bob's side to make sure that he's going to be able to handle, that when Alice indexes into Bob's bit string for coordinate I, that Bob will be able to support both bits. And then we speak. And then we keep going. As long as Alice speaks, we cannot issue a query, right? There hasn't been a round yet. So we just have to keep going. Finally, Alice stops. Okay. Then what do we do? Then we query Q in order. So this is an ordered queue. So we query the coordinates in the order they were entered. And this gives us a Z Q living in 0, 1 to the Q, right? This is actually the decision tree query. We have no control over what this is. This is we'll get through that. So now what do we do? Well, or rather now is when we do it. Sorry. So here is, I mean, when we do the cleaning up, we clean things up on Bob's side in order. So now we know what we got, right? We actually know whether we need a 0 and a 1. So therefore, for these coordinates in order, we're going to update B so that Bob can, we know that what Alice is indexing, right? So for these coordinates in order, in coordinate I, we know that Alice has an integer in this set. And for all of those integers, we need to be able to support Zi, which is what we got back when we queried.
In this be intersection over all line.
It's a for loop, right?
Oh,
But there's again, I do this in order, in the same order that I did these calculations. Okay, now we're done. Alice is done speaking. And Bob is, relatively speaking, less problematic. Okay. So this is like, now while Bob speaks, the big while loop still continues here, but while Bob speaks at V, we need to decide what Bob is speaking. And again, we know that Bob is going to move to, the consistent set will now be B intersection, not X, but Y, YVB, if Bob speaks bit B. We just want to make this as big as possible. This is the least informative thing we can do. So this is the bit that Bob speaks. So we update B to B intersection YVB and move to VB in the protocol tree. Interestingly, we're on Bob's side. No, don't worry about cleanup. Okay, and this is what we will do until we hit the leaf. And then we just return the answer at the leaf. Okay, I'm wondering. So we've been going for what, like an hour now? Is this a good time for a break, or do we want to continue for a few minutes? What do you say?
So it's a good time for everything.
Good time for a break. Do we have any questions about the evaluation algorithms? Like everything that now, like everything is in place, all the definitions are in place. The minor thing that remains is the proof correctness.
Yes, I do have questions. So I didn't really get what the project subroutine does.
Yeah, maybe let's see. So the red things are in red because they're a little bit magic at this point. So let's start from the bottom just because I don't remember if I even explained. So prune was just to saying that when Alice speaks, so A is looking very nice here, but I don't know how it is affected when I take the intersection with when I move down to the inputs that are consistent for the node one low level down. And in particular, maybe my degrees will go bad now. So prune is basically saying, oh, if in my graph I get some right vertices of low degree, then that's bad. Let me clean that up.
Okay.
Because so this I did not say. So throughout, okay, I'll do it later. So what project does is we know now that we have to query I. We don't yet know what. I mean, it might take quite a while before we're just scheduling the query here. I mean, Alice might be speaking for a long time. So what I'm just doing here is I'm looking somehow intelligently at my input on Alice's side, and this is the current input on Bob's side. And here I'm basically just trying to figure out what is a good set of indices in the ith coordinate on Alice's side that maximizes the probability that Alice and Bob will be able to support both 0 and 1 answers from the decision tree. Because what this set is what am I going to use this project set for? So firstly, I'm going to say Alice will restrict in the ith coordinate, so she only has values from UI. And this Bob knows. So then Bob uses this UI to say, okay, let me make sure that on UI, I can support ones everywhere and that I can support zeros everywhere. And these are C1i minus I and C0i minus I. And then Bob will take the intersection of this, which sort of, at this point, we're sure that if these sets are large enough, UI will be a set where once we know what Zi is, Alice will say, well, I'm only telling you that I have some integer in this set, and Bob will say, yeah, I can support a 1 everywhere, and I can also support a 0 anywhere. So you don't have to tell me where in this set you are.
Okay.
Does that make some sense?
Yeah. Other question, why is it, I mean, I guess on an intuitive level, well, I guess I don't know. Why is it so important that we query Q in order? Line 10 and 11.
Line 10 was me just typing. It's not, I mean, this is, yeah, I misspoke. I mean, we're just issuing a parallel query to the decision tree.
Ah, okay, you mean parallel. Okay.
So
sorry, when you said in order for me, it was a
yeah,
okay.
No, I'm just quick. I'm sending off like, hey, dear input, tell me these coordinates.
Okay.
Here, why I'm doing it in order is sort of because this is, I computed the CIs in this order, so it's sort of, it just needs to match up.
Yeah, I guess I can.
I've sort of made sure that the first coordinate, I can deal with that in this way. And then, okay, given that we've already given up on the first coordinate, then I have the update for the second coordinate and the third coordinate. And it stands to reason that somehow here, B and C will sort of, B and C are kind of syncing up here, right? You see that?
Okay.
I mean, CI is, notice this is like important that here is where we're picking out that I'm able to support a result of B. And once I know what that result is, I have exactly the same thing here. So these are just, here is where B is syncing up with C. But importantly, C sort of for auxiliary reason, it lives in a much smaller space. B actually lives everywhere, and I'm just working on the ith coordinate. But B lives in the full space, and A always lives in the full space. It's only C that lives in the space of non-queried coordinates.
Oh, so, yeah, okay, but sorry, stupid question again, but like, so you construct those BIs on line 12. Where do they appear again? What do you do with them afterwards?
I basically, I'm updating B.
Ah, you have the. Yeah, sorry, BI.
This is Bob. This is just Bob's inputs. So this is at all times in the simulation. I have a set of possible inputs for Alice.
You're updating
possible
these.
inputs for. So this is just
2 dots. Okay, yeah, sorry, I just misread. I thought it was BI equals. No, it's just. Yeah. All right, yeah. Okay. Sorry, yeah, just misread. No. Thank you. Not that one. Yeah, okay, that makes more sense. Okay.
The size of project is supposed to be small compared to
You will want it to be medium large.
Oh.
Yeah, it's sort of there. I think there's a little bit of tension here in the. I mean, so sort of the larger UI is, the better in shape we are on Alice's side, right? But somehow, but the larger UI, if UI is super large, then we'll have a massive collapse here probably. Like, because the larger UI is, like the larger UI is, the larger A is here, and we are worried about Alice and her flexibility. On the other hand, if UI is gigantic, then this thing will be fixing pretty much all bits to a particular value, and then I can worry that this set gets very small.
But we are about to query this thing anyway, right? So after we have queried the coordinate, why do we want Alice to have lots of freedom in that coordinate? Like UI is
No, I want A to be large. A lives everywhere.
Right.
Because I'm going to continue to use A for like future queries. Okay. So the plan is now let's take a break. And then we're going to state lemmas what prune and project satisfy. And then we're going to try, so given these lemmas, we'll argue why this is correct. And then let's see, basically, let's see how far we're able to get into the proof before we get too tired. Let's take a break. Okay, so we're back. We have gone over the algorithm that takes a communication protocol and issues queries to the bit string Z, and will compute a queue such that ZQ is in the search problem, search relation S is the claim. And we would like to argue that, okay, so we want to argue that this is correct. We want to argue that the number of rounds is correct. We want to argue that the number of queries issued is correct. The reason why it would be correct when we're reaching a leaf is sort of intuitively because then we hope that at that leaf, whatever input we have should be consistent with the inputs that Alice and Bob had. So it's sort of, you can try to do a cheating proof that once you reach a leaf, because of correctness, like everything should be fine. That's actually like blatantly false. You have to work a bit here, but we'll get to it. I'm mostly going to skip it. The number of rounds, I think, is clear, right? I mean, we only issue queries when Alice stops speaking. So, like, by definition, this parallel decision tree will have the right number of rounds. What is not at all clear is how the number of queries relate to the total communication, or at least not to me. Okay. And it's not at all clear what project and prune does, so let's talk about that. Some key definitions. So one thing that we want to be true on Alice's side throughout the proof is thickness. So when we're looking at this graph where we say, oh, if Alice has to commit to all other coordinates, how much flexibility is there with respect to I? Then the answer is, well, quite a bit of flexibility, at least L to the 2/3. Okay, so L to the mu, where we can pick mu to be 2/3. We'll maintain that for all coordinates in I. Okay. Obviously, for the coordinates where we queried, those we have already left behind us. We don't worry so much. And what happens is that when Alice speaks down here, and we move to the subnode and the consistent inputs there, then we might lose thickness. Okay, so the prune method restores thickness. Let's see what it does. It's called the thickness lemma. If it holds that the average degree in all coordinates that are alive is somewhat large, L to the lambda over 4. Remember at the beginning here we actually had L to the lambda is our guarantee at the beginning, but we're asking now for L to the lambda over 4. Then prune will return a subset A prime of A, for which two things hold. That A prime is thick, so it has no bad right-hand side strings for any coordinate I that is still live, and we have not, when we prune, we do not lose the density too much. Okay, what's the density? The density of A living in I is basically minus the logarithm of best possible. So actual case minus divided by best possible. So size of AI divided by the full size, which would be L to the size of L. Take the logarithm of that and take a minus. That will be size of I times log L minus log of the size of AI. Okay, and AI will often be actually the projection to I of A when we use it. So clearly at the beginning, the density loss is 0, right? Because we have equality here. Also, this is always smaller than this. So the density loss is always non-negative. Yes? Okay. And here the beta is the same corresponding density loss on both sides, which we will not be so worried about. Okay. So the thickness lemma restores thickness, and obviously you could restore thickness by throwing away everything, right? That, I mean, an empty set is very thick somehow. But we restore thickness without throwing away too much. So density loss goes up by at most 1, and these additive ones are basically, I mean, that's a factor 2 in the size of this set, right? So whenever you have like a factor 2 loss here, that's a +1 here. Okay.
Factor L loss.
So again,
A factor L loss. Like a factor L loss in AI makes alpha global.
Well, it's a 2 logarithm, right? So I think I stand by what I said. This is the 2 logarithms.
Yeah.
So okay, and then we said that when the protocol has leaked too much information about the coordinate, which is when this average density goes down, then the project method restricts Alice's input to a set such that Alice will be dense in the remaining coordinates, and we also want to make sure that Bob can support whatever the query, whatever the decision tree query will give back to us. Okay, so this is the projection lemma, and the projection lemma says, suppose A is thick in the live coordinates. And suppose Bob's density loss is not too bad. Okay, this is a number. Then the index set for Alice for coordinate I returned by project satisfies three things. So firstly, if I now sort of remove, so what will happen now is we're going to remove the coordinate I, right? And if I first I sort of prune A so to only save the integers, only save the vectors that have coordinate I in the set U. So first I prune and then I project, then I'm still thick. So this makes things thinner. Projection, we know, makes thickness good. The sum of it all is that we restore thickness. And then you can ask, okay, but how much did we lose in terms of density? And in fact, density loss improves, right? So we have the previous density minus log L plus log the average density, and this will be a smaller number. We'll get to this. And then, interestingly, so what I'm doing now is that for all the other coordinates, I'm maintaining vectors that can be extended to both ones and zeros of coordinate I. So I should be very nervous about what happens when I take this intersection, but it turns out it's not so bad. You see, we actually lose only one in density. Which is, again, a factor. Okay? So the claim is, and one thing we're going to use also, we're going to look at density loss. And you could also ask, like, what happens to density when we go from A to A intersection this? And density loss goes up by at most an additive one here, right? Because we're picking the larger one of these subsets, and we know that they cover A. Okay? And the same thing here, we know that density on Bob's side, density loss goes up at most by an additive one. Okay, so with this, we can finally state then the simulation lemma with everything parameter. So the simulation lemma says the following, that if a deterministic, so we're in the deterministic communication, right? So if a deterministic communication protocol pi solves the lift of S of length m to the 3 plus epsilon for a positive epsilon in less than r rounds, less than c total communication of unication. Okay, then where let me actually say that c should be less than m over 2. Sorry, I forgot about this. 1 minus lambda log L. We'll talk about this in a bit. Notice that this is this upper bound is like this is a bizarre amount of communication. You should think of like if the protocol is communicating more than this, then we really should not have to worry. But we'll get to it in a bit. Okay, so if this holds, then eval pi encodes a parallel decision tree of depth at most r and total query complexity is at most 2c, plus we even save a log factor, so 1 minus lambda over log L. This is the formal statement. about this condition? Well, lambda is like really, really small. Log L is going to be large. Again, L is, where do we have this? L is m cubed, more. So pretty much this will pretty soon be larger than m. Okay. So if the simulation theorem for more than this communication, then I just do a decision tree that queries all the coordinates in one row and gets the answer. And that satisfies. I mean, that's at least as good as this. Okay.
But there's also a by-log in the query complexity, right? So,
yeah, but you have. Yeah, but these guys cancel, and this two takes care of this two, I think, right? I think we're fine.
it's just a login factor.
I mean, this matches exactly this. No?
Okay.
Okay. So some pieces of notation. So we already know that V is the node where we currently are in the communication protocol. We already talked about that XV, X super V, and Y super V are Alice's and Bob's inputs that are consistent with this. RV, I just define that to be XV product YV. And it's just a basic fact of deterministic communication that the set of all consistent inputs at this node is just the Cartesian products of Alice's set times Bob's set. There's no like dependency between them. This requires an argument, but it's a standard fact in deterministic communication complexity. Let me denote CVA is number of bits sent by Alice up to V, and CVB is number of bits sent by Bob. Okay, and I will maintain here A and B are, I will always make sure that A lives in XV and B lives in YV, but they will be cleaned up so that they have nice properties. Okay? So now I want to argue that this algorithm proves this simulation lemma. For now, we're taking the thickness lemma and the projection lemma on fair. Yeah. And the proof is by stating some invariants that hold always. So it's always the case at all times that on Alice's side, if I project A to the coordinates that are still alive, then that's thick. It is always the case that the inputs of Alice and Bob that we are considering in our simulation are in fact a subset of what Alice and Bob would have used in a real communication when they reach this node. Here comes an important invariant. M minus I, what is this number? This is the number of queries we've issued so far. Okay. So I want to upper bound this, and we claim that at all times, this is actually upper bounded by how much Alice speaks divided by 1 minus lambda log L. And then we need to keep track of, so one thing we can be nervous about is that we're hitting the C set fairly aggressively when we're trimming and trimming and trimming, and need to be able to deal with two answers because we cannot yet issue the query. And this is something new compared to, like, I don't know if there are any other simulation papers where they have this round efficiency. So this is, by the way, also maybe a nice question to look at the lifting literature and see what other nice lifting terms are there where some round efficiency could give you new applications. Because all the standard works don't have round efficiency. And we have to work on the C guy and make sure that it doesn't get out of control, to wait to issue queries to the decision tree until at the end of a round. So it's important that the density of CI is not too bad, meaning the density loss must not be too large. So how much density loss are we willing to accept? M minus I. Again, this is the number of queries we've issued, plus how much Bob speaks. So these invariants should be true at all times. And then we have at the start of a round, either for Alice or Bob, we want two more things to hold. At the start of a round, we're going to look at not this C set that is a proxy for what Bob is doing. Now we look actually at the density of Bob's actual set. And we want to say that the density loss is not too bad. Exactly same as for the proxy C set, as you can see. And then finally, and most importantly, for all I that have been queried, it should be the case that, for all indices that have been queried and for all xy in AB, this is not A comma B, this is the Cartesian product AB, it should hold that if I index in coordinate I, then I should get back what the decision tree said. This is the way we know that we're simulating what Alice and Bob could have experienced if they actually worked on a lifted version of our problem.
So by at start of round, you mean at end of proving? Yes.
By the start of a round, I mean when Alice speaks or when Bob speaks. So Alice speaks here, Bob speaks here.
Oh.
Yeah. Thanks for the question. And basically these, so I1 through I4, I'm going to restore it every round. I5 and I6, I just sync up whenever it's time for Alice and Bob to start speaking. Okay. And now we're running out a little bit of space. So maybe I'll use 3 boards. So now basically I just want to argue, it's going to be key to say that we maintain this throughout the algorithm. Okay. So let's look at invariant I1. When is thickness affected? Well, when A changes or I changes. And you just go over this and you realize that A changes here. And I also changes here. And A changes here. And that's it. Okay, so line 7 and line 9. So So maybe let's do this first thing carefully, and then you see how much more you want of this. So at line 7, we have thickness. When we enter line 7, this is by assumption. Like after every line, we have this invariance. So at the start of line 7, we're thick. That's the inductive assumption. And according to the lemma statement, we have that the total communication up to this point is great. So I erased the lemma statement. That's brilliant. The total communication is, okay, this is really annoying. With some slack, it is at most m log L. And one of the parameters that have been floating around is gamma. And gamma I set to 1 over 3 plus epsilon. So m is just L to the gamma log L. So the communication is not too bad. If we put together invariants I3 and I4 and look at the density loss for B, so the density loss for C at this point is at most this, and M minus I is at most this. So we get that the density loss for the proxy for Bob is at most 2 CVA divided by 1 minus lambda log L plus CV. So CVB is this, and then I just plugged in invariant 3 to get this. Which in particular will be smaller than CVA plus CVB, which is smaller than the total communication, which is smaller than L to the gamma log L. Which means that when we run the projection lemma, A was thick, and the density loss for C was not too bad. We even have some slack. So the projection lemma says that what the projection lemma says is that this set is thick, right? So P1, property 1 of the projection lemma says that IA remains thick. Okay? In line okay, so line 9, what's happening there? So we had thickness, but then we're intersecting A with X, and we're pruning. So again, then we need to see, is the thickness lemma condition satisfied? And the answer is that, well, we exited this while loop, right? So at this point, all average degrees were actually at least L to the lambda. Yes? Okay. How much did the size change then we took this intersection? Well, I took the larger one, I took argmax, so at most by a factor 2. And that means that if I just write down, okay, so the average degree, just by definition, AI, is the number of edges. Actually, so let me write it right away. So the average degree of the graph I is number of edges divided by non-isolated vertices. So if we just plug in this new thingy, we have now, we're projecting to I A intersection XVB. Sorry, we want to understand what this average degree is. And the answer is that that's the total number of edges which is this, divided by the number of non-zero left vertices. What are the non-zero left vertices? The non-zero left vertices we did this last lecture. This is basically what you can get if you just project out the ith coordinate. Okay. So the average degree is exactly this. So like the total number of edges divided by the number of non-zero degree right vertices. And let's see, so now we just need to do the math. So this, I claim, is going to be at least a half of projecting A, right? Because we picked the bigger half. And also, I mean, here, if I project all of A, I can just make things larger. This is larger than this. But now, this is also an average degree, right? This is the average, this is now half of the average degree for pi IA. And what was this average degree? Well, we exited the while loop. So this was at least n to the lambda over 2. Okay? So let's see, what is it that we want to... so now we want to apply the pruning lemma, and we see that even with some margin. So our lemmas are like stronger than we need because we're actually doing them for the real communication case. So the thickness lemma conditions apply. So then we see that we will return a pruned A set, which is thick. Okay, so this takes care of invariant one. Should we do the other invariants in detail, or should we try to fast forward a little bit?
2 is clear.
2 is kind of obvious, right? Because we started, this is always true. And whenever A and B change, I mean, either they're shrinking like this, and then it remains true. And whenever we move in the communication tree, then we intersect. So this is kind of clear.
6 is also clear.
Yes.
Yeah.
So 3 is a little bit interesting. So basically, let me just tell you what you So maybe talk a little bit about 3. I mean, that is somehow, that is making sure that we don't talk too much. Right? Sorry, that making sure that Alice and Bob talk enough. Right? The number of queries is upper bounded by Alice's talking. So this is an important invariant. So let me say something about it. So it's sufficient for us to show that, let me just measure the density. And suppose I can prove to you that the density is at most 2 times what Alice has spoken, minus the number of queried coordinates, times 1 minus lambda log L. Okay. Suppose I can prove this to you, then you should be happy. Why should you be happy? Well, because density is non-negative. Okay, and then you see we can just divide through by 1 minus lambda log L. So what we want to show clearly at the beginning, density is 0, which is, density is 0, no queried vertices, Alice has not spoken, so this is true at the beginning. And then we want to say that when Alice sends a bit, whenever Alice sends a bit, we're willing to take a density loss of 2, but not more. Okay, and whenever a query is issued, so that this m minus I increases, right? This is the number of queries. Then we want to say that the density improves by 1 minus lambda log L. Okay, so why would this be true? Well, whenever Alice sends a bit, let's see, where does Alice speak? So here, right, 8. So here she takes the intersection, that loses density of 1, and then the pruning lemma, the thickness lemma says we lose 1 more in density. So 1 plus 1, that's 2. Okay, so then when Alice speaks, we've said that yes, we lose, Alice speaks only here, and then indeed we lose 1 plus 1. And in the let's see. So according to the projection lemma, let's see, in P2 in the projection lemma, then the density loss changes by minus log L plus log average degree. So minus log L plus log average degree I pi I of A. Am I copying this correctly? Yes. Okay. And now the point is, so this is the same as minus log L. And what was the average degree? The average degree was pretty small, right? So it was at most log L to the lambda. And now things comes together, and this is at most minus 1 minus lambda log L. Okay, which is exactly this factor that we want to pick up. Let's see if we can say anything interesting about I4. So CI is, so there's a sort of a bit of an interaction between I4 and I5. So first CI is updated here, but at that point we know that the invariant holds for B. So we're just copying CI to B, so then it's fine. And at line 7, we already argued that the project lemma was fine. And the projection lemma item 3 says what we want to say, right? We issue one more query, and we're losing density at most 1. Invariant 5 for Bob, that's pretty easy because nothing much is happening. It's sort of whenever Bob speaks, we lose at most 1 bit of density, right? So this is like, because we do argmax here, we pick up at most 1 bit. For Alice, if Alice is speaking, then basically you need to set up notation. Basically, when Alice speaks, the reason that it holds I5 is that these guys are synced up. So we're sort of, when Alice speaks, we're updating CI in a very, very conservative way, and we're able to pick both bits. Okay? Then we learn what the bits actually are. Then we kind of do the same update, except we don't need to do the intersection. So since already for C, the density was good enough, it's definitely good enough for B. I mean, the really, like, the point is that these blue boxes, like, we're performing exactly the same operation. So you just say, you sort of sync them up step by step. And this is why, for proof reasons, we really want to do them in the, if we do them in the same order, then we maintain the invariant that, you know, the density of this guy is at least as good as this guy. Because formally speaking, the projection of this guy to the currently relevant coordinate set is a superset of this guy. Am I making some sense? Okay. And fine.
There's some type issue, right? As in CB is defined only on I minus I, and B is defined on the entity.
Okay.
That's mostly a type issue, right? As in, isn't B exactly the same as CB I minus I here? So in the end, in line 12, whatever value of B you get, wasn't it exactly the same as CB of I sub?
I mean,
so in the end of line 7, you get
yes.
some CI, right?
Yes.
And B isn't B exactly the same thing? Just
no, B and CI are like, no. So B can be larger, firstly, and they live in different spaces, right?
Oh, yeah,
B lives in the I space only, B lives everywhere.
Yeah.
Plus, B can be much larger, right?
Oh.
B can be much larger than C.
But you are taking this chi, I, y, z, I, aren't you?
But for C, I did it for both.
Ah, right.
Okay. And the reason that this is like another key invariant, but again, this is what happens here at line 7, right? This is where it's so important to line up. At line 7, Alice is committing to, in the ith coordinate, she will only have integers that are in UI. Okay? And then Bob makes sure that, well, in all those coordinates, at the same time, he will be able to support wherever bit we need, which we fix here. So sort of just by construction, if you look at it carefully, this is why invariant 6 is 5. Is this believable? Okay, fine.
Oh, I see the reason for taking the intersection. We want to make this a parallel query.
Yes.
Yeah,
The round efficiency is a big thing.
Yeah,
yes.
yeah.
Otherwise, we wouldn't have a problem. Otherwise, we would update B at the same time, but we need to maintain round efficiency. Okay, so I claim now it's clear that when we reach a leaf, again, the number of rounds, it's obvious. What is the total amount of communication? Well, it's actually upper bounded even by Alice's communication. So this gives us the claim in the simulation lemma. So the total number, yeah, so the total number of queries is fine. What we don't know is obviously the communication protocol has a fixed answer queue in mind now, right? We have reached the leaf. And now we have to argue. So we know at the leaf, pi answers q. Okay. And what we need to show is we want to show that there exists a tuple xy in A cross B such that if you index y using x, then we can get z, which is the actual input. Because if we can show that there is some input that when you apply indexing, you get z, then in that case, that would mean that q is a valid answer for z. Okay, but this we need to prove. This is not obvious. And basically, what you need to do for that is you sort of keep going, you sort of at the leaf, you start querying. You now have a bunch of coordinates that you have not queried. Like we know that the indexing is fine for all the queried coordinates, but maybe there are many coordinates that we did not query. So then we sort of in our head start querying them one by one and still use the same machinery with projection to argue that we can sort of deal with whatever zi's are thrown our way. But this requires a proof.
Oh, sorry, doesn't I6, sorry, I missed that. Why doesn't I6 automatically ensure that for all x and y you agree on whatever?
I haven't, there are many coordinates that I haven't asked.
No.
So,
But the contradiction will be on the queried coordinates only, right? So,
no, we need to prove this, and it requires an argument. There's no way around. So, okay. So maybe, what can we do? I could tell you at least what prune and project are, and we can hand wave. The thickness lemma is not bad. I think I will be able to hand wave it convincingly. The prediction lemma is worse. Okay. I'm just trying to understand now if we need any of the invariants, but I don't think so. Or are there questions at this point? Are there questions? So, like, why did I need to find Z? Well, because there are lots of coordinates that we have not queried. And a priori, I mean, we have no idea why this. We need to know that Z is, among the lifted inputs that end up at that leaf. Otherwise, we have no idea that this is, in fact, the correct answer.
this is the analog of this full image lemma.
Maybe, I don't know. Okay. So, what pruning does is the following. So let me just for bookkeeping purposes, let me now actually project out A to the coordinates I, and note that this is a very different set from this set. Yes, it lives in a different space. And then I just do basically, what do I want to do? I want to restore thickness. So while there exists an I such that we don't have thickness, so if I min I, AI, less than L to the mu, where I think I picked mu to 2/3 before, then well, there is some low degree vertex. Okay. So let xi minus I be a right vertex of degree less than L to the mu. And then I just say, throw it away. We can't keep it, right? So I just set AI to be all xi in AI except when I project away the ith coordinate, I shouldn't get this guy. Maybe it's a better notation if I like put a start. But basically here, I do the stupidest thing I could imagine. This is a low degree vertex. It must not be there. Remove it. Right? All vectors that in the ith coordinate, all vectors that when I project the ith coordinate where the remaining coordinates are this problematic string, they have to go. And then once I'm done, I return. Now I'm back to the original space. Now I'm in the big A space. I return all x's in A such that when I project them down to I, they survived this massive cleansing procedure. Okay, so this is proved. So I claim by definition, whatever I return is thick. But it could be empty, which would be a little bit sad, right? So the thing I need to argue is, no, but the density is not too bad. Yeah. And this is the time where I actually need my, so we need some magic constants. Some of them we've said. Let me just quickly, again, the lift size is m to the 3 plus epsilon. Gamma, I think I introduced before, is a sort of inverse of this exponent. And now we need lambda, delta, and mu in 0, 1, such that lambda minus mu, gamma is mu. Mu was the min degree exponent. I also want mu plus delta minus 1 greater equal gamma, strictly greater than gamma, and gamma plus delta smaller than 1. Basically, I can just plug in the numbers I had. So let's see, gamma is this, delta and mu can be 2/3. And then lambda is basically going to be 1 minus epsilon, and then you tweak it a bit so that this holds, which you can do. The notes have all the details. So maybe I won't dwell on this. So, okay. So the number of non-isolated right vertices is like for any I graph, this is the number of edges. And then if you just plug in the number of edges and you divide by the average degree and you look at the definition, if you need to, then this is the number of non-zero vertices you have. This is really just plugging in the definition and this pops up. Okay. So this means that every time in the loop I remove a non-isolated right vertex. Okay. So for the ith coordinate, I cannot iterate more than this many times. And this since we exited the while loop at 5, let's see where we exited the while loop and then we're shrinking by factor 2. This means that this average degree, so like this, let's see. So let's just write it down and see if we can do the math. I claim that we get pi I of A, and then the average degree now will be L to the lambda, and I lose at most a factor 2. And now if I sum over all I, then the number of iterations will now be, so that's the 2 that I move up here, and then I, the size of the projection, divided by L to the gamma, continuing to bound. This is I is at most M, which is L to the gamma. So I guess at most 2 times L to the what is happening now? This should have been this is typo, this is the lambda, right? Now things make sense. So I pick up a gamma and a lambda. I of A. Okay. So I claim that this is the total number of iterations of this while loop. Okay. And now the question is, how many elements do I remove? Well, at most this many, right? Okay. So then the total number of removed elements from A is less than 2 times L to the mu times L to the gamma minus lambda, and carrying around this projection. But now let me rephrase this. This is like gamma plus mu minus lambda, right? So let me write this. L raised to the power of gamma plus mu minus lambda. Yes. So if I take this, then I see that gamma plus mu minus lambda is negative. So, and I mean, L is somewhat large. So if I just pick my values to be large enough, this is going to be pi I a divided by 2. Which means that I have my thickness. Questions on thickness? Or we're starting to feel a little bit thick in the head, all of us? Okay. So we won't prove projection, but let me just tell you what happens. It's basically the algorithm. I mean, here it was pretty brain dead. Projection is going to be even worse. And it's really stupid, and the whole thing is to analyze that this actually works. And this analysis is not trivial at all. But let me tell you what the algorithm is. So here comes the project algorithm. And then the analysis we can talk about some other day. Okay, so we somehow need to find a good set U, one that will maintain what do we want it to do. We want it to have all kinds of magic properties. When I first restrict to U but then project, I restore thickness. I don't lose too much in actually density improves. And also, and this is the nervous part, like if I pick U badly, I would expect these guys to be really small and their intersection to be even worse. But their density is also almost what I had before. So how, okay, any ideas for how I should pick such a U? It needs to have all of these amazing properties. We need to do something really, really clever.
Random.
Yes. So we pick a set of size L to the delta uniformly at random. Okay, and here we go. Then, you know, for B in 0, 1, we compute CB to be the projection that we projected away little I of making sure that in the ith coordinate, first making sure in the ith coordinate, in all U's, in all integers in this randomly chosen set U, I want to be able to support a B. I do this for CI. Okay, I compute these two, and then let me set C star to be C0 intersection C1. And then I do the following. If now it turns out that beta of C star is less than beta of Ci plus 1, and if it also holds that pi I minus I, again projecting away the ith coordinates, after first having restricted Alice's inputs in the ith coordinate to U, if that is the same as pi I restricted by pi projected to I minus little I a. So if these are actually the same, then I return U, else I guess I call project. I return project A P I. I try again. So basically, I just pick something random. And this is going to work. And there's the easy claim and the hard claim. And the thing that you need to, so let blue be, let the red be hard. This requires a lot of work. And we won't do it. I think maybe we won't do anything more. It depends on you guys, but I think we're maybe want to wrap up. I can tell you what the argument is here. So basically the argument is, so I have this graph. Here is the graph I. And here are all the indices. And here are all the complement vector indices, right? Is this, I mean, this is a little bit improvised, but you maybe get the general idea. So the first thing that will happen now is that so I will pick U at random, okay? So U is maybe now, this will be U. But U is fairly large. And U is at random. Okay, so now I drew it this way, but so what you do know is that all of these guys have fairly high degree. Okay. And you know that you have this equality if we're so lucky that one of the edges from here actually goes into U, then this set will survive. Right? And now the argument will just be, well, all of these degrees are fairly large. U is completely at random. When you choose it at random, what's the probability that you miss all of these edges? It's low. In fact, it's so low that you just do a union bounding argument. And you argue that for random U, you're going to hit all of these non-zero degree vertices. Okay? And that means that they all survive. Obviously, like, we're losing edges and stuff, but they all survive. And then anyway, you project out these coordinates, and then you don't care about this side anyway. All you care about is that this guy survived, and they all survive. All the non-zero degree vertices in here had an edge into U by a union bound argument, and therefore they survive here, and then I project away this part, and they are still there. And I think that there are some more details. So basically, I don't know. So this is the one of the technical claims, and this will then take care of basically what you need to argue about is you see that you're arguing about density of these guys, but basically from the invariant you have and from the fact that this guy is the same as this guy, right? And you know that pi I of A was already thick and fine and everything. And what did projection do to thickness? Could only improve it. Okay. So by the fact that this is equal to this, and this was thick already before projection, this sort of tells you that this guy must have nice properties. Okay. this is not at all obvious, and yeah, this is sort of where the main part of the work is, which Mark Vinyals and Susanna Rezende did. Okay, so I think maybe, yeah, should we take a break and continue for 1 more hour? Or do you feel like maybe we got a sense of roughly how this goes, and it's, you know, it's time to call it a day? We've had a good discussion and we learned stuff, but all good things come to an end. What's your feeling?
Yeah, I think it's okay for today.
Okay. So, questions about this? Comments? Everything is crystal clear? So, yeah, I think just to stress that so far, I don't even know if we got to a point where the difference between, yeah, no, we did. So, I mean, where are we using that we have deterministic communication? So it is kind of nice here that I think rectangles kind of behave nicely, and we can cut them, and we're sure. Also, when we have a rectangle and we intersect and we prune, it's makes our life easy. When we have these combinatorial triangles that Kilian talked about, then these operations become much more complicated. The reason that the lemmas, the thickness and the projection lemma, that they're not tight is that I think these are the parameters you want. I didn't say this. I don't know if you noticed. Like we were meeting the conditions in the lemmas with, you know, quite some margin, and that's because things are going to be much more subtle, much more tricky if you're dealing with combinatorial rectangles. And again, as came up in the discussion, if you are knowledgeable about lifting, if you know your Gauss, Pitassi, Watson inside out, like what's the difference? Well, the difference is, again, in this part where in a standard simulation argument, as soon as one coordinate goes bad, you query, you see what you get back, you clean up, update, and then you can continue. And the challenge for us really is that we know we need to query, we know the situation is bad, but unfortunately, Alice hasn't stopped speaking. And so this is why we go to all of these lengths of checking, okay, what do I need to do if the answer will be a 0? What do I need to know if the answer is a 1? Taking the intersection and now arguing that things just don't crash and burn and I lose everything. That is, there are some complicated combinatorial arguments where you really have to do the math. Okay, but I think that's it for today then.